Okay, let's get started. So today we keep talking about symmetric encryption, and we will discuss two particular algorithms which we are still using today. One is DES, which we do not use very often anymore. Another one is AES, which we still use every day. Every one of you are using it. And I also use them a lot in my research as well. So before that, let's revisit the design principles of block cipher. So in block cipher, all the designs, there are two principles. One is called confusion, another one is called diffusion. In confusion, we try to do substitution. That's same as in classic crypto. In diffusion, we try to rearrange the order of bits or byte. Anyway, the basic units there. Then we repeat this process many times to make it harder to find the correlation between the plain text and the ciphertext. Also, for each block we are encrypting, we try to split it into smaller chunks or smaller blocks. So this can be showing in this basic figure. So this is a figure of one round of a block cipher encryption. So you can consider this is the flow of one round. So a block cipher may have many rounds of something like this. So each round there is an input, then there is a key part. They do some kind of calculation, usually exclusive OR. Then after that, we get a string of bits. Then we separate them into smaller chunks. Then for each chunk, we substitute it with something else. So to substitute that, we usually look up in a substitution table, or called S box. After that, we're going to rearrange their positions, and to do that, we also follow a rule specified in a P table, permutation table. So that's the basic step. Then we do this multiple times. So most of block ciphers, they design following this structure. So I will just skip the formal definition part. So one way to realize this confusion diffusion paradigm is through something called Pfister network. So this is named after cryptography. I don't remember his first name. His last name is Pfister. So in Pfister network, each state, or let's say the state, we can say it's the beginning, the input of each round. So that part is divided into two parts. Divided in the middle, two parts. One is the left part, another one is the right part. So in each round, what we do is we first swap them. So the output from last round, the right-hand side, goes to the left-hand side of this round. Then the right-hand side will do some encryption or calculation, which is the left-hand side from the last round, exclusive OR, with the key, and the right-hand side goes through some Pfister function, go to a function, okay? So if we draw a figure, it will look like this. So for each round, we have the input. We divide the input into two parts, left-hand side, right-hand side. The right-hand side directly becomes the new left-hand side. Also, it goes to a function. So the function takes some bits of input and key of the input after this function. So this function obviously will do substitution and permutation there as well. But also you can say here we'll also do another additional permutation. We swap the left and the right. So after that, the output is exclusive OR with the left-hand side. So this is a very simple structure. We can write it down in an equation like this. So as you can see, what we're not really showing here is the function f. So this function f obviously has to be carefully designed. It has substitution modules and also permutation modules. If we do not choose them carefully, let's say if the substitution doesn't do anything, the input directly becomes output, we do not really substitute that, then it's a weaker password. So the design principle here is we use a S-box. The purpose to use an S-box is, first of all, it will be much faster. What to replace, you can just look up the table. So it's an O1 operation. And the principle here is the S-box. For any bit change in the input, the output from the S-box should have at least 2-bit changes. The permutation step has a similar rule. If there is the 1 bit of difference in the S-box should propagate to at least 2 X-boxes in the next round. So that is the principle of diffusion. We want to have 1 bit of change to influence more bits in the output. So from attacker's point of view, you look at the output, it's harder for you to infer what is input. Also in block cipher or those kind of symmetric encryption, larger keys usually means greater security. But also in last class, we say that larger keys do not necessarily means greater security. You also need to make sure your algorithm itself is secure. So if your algorithm is perfect, it's secure. It doesn't show you any statistical information between the input and output. The only way attackers can break your system is to brute force. It guesses all the keys and try to decrypt the message. Then after that, it just say the plain text to say which one makes sense, right? So that's why for n-bit keys, on average, the brute force will take 2 to the power of n divided by 2 times for the attacker to crack your system. On average, obviously, if for attackers to really crack any ciphertext, they should be 2 to the power of it. And also the experience tells us if we have more rounds, more substitutions, more permutation, then usually your algorithm will be better. Also, larger block size offers increased security. So those are the experience we learned, the lessons we learned. So next, we will look at 2 particular algorithms. One is called a DES, Data Encryption Standard. Another one is called AES. Those are the algorithms have influenced the design of block cipher for decades. DES is not used anymore. It's replaced by AES. AES has been used for 23, 25 years. Used everywhere. Everyone is using it. You have a laptop, you are using it. So DES was first developed by IBM back in the 70s, then adopted as a standard also in the 70s. So usually how it works is some organization like National Institute of Standards and Technology, they will publish a solicitation for crypto systems. So they did it in the 70s, they did it again in the 90s. And what they ask for is a new encryption algorithm that can replace the previous one. Then they have some funding available, then the research teams will propose their design, and hopefully their in the hopes that their design will become standard. So DS was standardized in the 70s, and it was expected to be user standard for 15 years. Actually, it was used much longer than that, almost 25 years as a standard. So in early 2000 and also late 90s, NIST, they have come up with a new solicitation to replace DES. Then the algorithm they propose is called AES, but there were multiple candidates, and finally one candidate win. Then we call that AES. So the DES algorithm, the key size is 56 bits. This number is a little bit weird, right? Right now, when you look at any number, it should be 64 bits. It should be several bytes, right? 56 bits is not really, well, it's 7 bytes. 7 bytes is a little bit weird. Usually we look for something like 8 bytes, 16 bytes, right? So the key, but it was designed that way. So the key size was 56 bits. The block size is 64 bits, which means what the algorithm really encrypt is 64 bits or 8 bytes. Even though the key is smaller, but the each block is 8 bytes. So if you want to encrypt something much longer than 8 bytes, like you encrypt a file, which is 1 megabyte, you encrypt a video, which is 1 GB. What you do is you divide that into 8 bytes per block. You encrypt each block. Then you do some operations between the block. That is what we will discuss about the encryption mode part. So DES has 16 rounds of operations. The substitution, the permutation is 16 rounds. So those 16 rounds were performed on each block, which is 8 bytes. So previously, what we discussed here, everything here is inside that 8 bytes. The 8 bytes will go through something like this. Okay. So DES uses the faster network. It has a basic structure like this, which we already discussed. Actually, AES do not use this structure anymore. AES is much faster and secure. And one of the design goal of AES is you should be very fast. So in DES, the left-hand side and right-hand side each, because the encryption, each block is 8 bytes, 64 bits. So when we encrypt that block, we divide it into 2 parts, left-hand side, 32 bits, right-hand side, 32 bits. However, the key is only 48 bits here. For each round, the key is only 48 bits. So there will be some padding to make it longer, actually. So the master key is 56 bits. For each round, the key is only 48 bits. So let's say this G here is this faster network. So what AES does is 16 rounds of those faster network. Each round use a different subkey, like from key 1 to key 16. So obviously those subkeys were derived from the main key, which is 56 bits, and each of this is 48 bits. Then inside that, there is a F function which has substitution and permutation. But at the beginning of the going into those 16 iterations of the function G, there is another round of permutation here. And after that, then will be a reversed operation of permutation. So that is a basic design of DES. So DES is standardized, but the design principle, the design rationale behind it was not really disclosed at the beginning. So there was a lot of mystery in the design. People do not really understand why it was designed that way, especially the S box we will look at later. So the F function look like this. So in each round, the input, the key, will go to the S function. So the S function at the beginning, what we have? We only have the right-hand side, which is 32-bit. Then the 32-bit will be extended into 48 bits. That 48 bits will just do a simple exclusive OR with the subkey. The result will be another 48 bits. Then that 48 bits will be divided into 8 6-bits. So this part will be 48 bits and 8 chunks. Each chunk is 6 bits. Then for each chunk, there depends on the position. Okay, the first 6 bits will go through the S box 1. The last 6 bits will go through S box 8. So there are 8 different S boxes. So S box is just a substitution table. Given an input, give you another output which tells you to substitute the previous one, right? There are 8 different substitution tables. After that, 6 bits of input are substituted into 4 bits, okay? Not 60 bits anymore. But remember, the input was 32-bit. It was extended to 48 bits. Now, the 6 bits was changed to 4 bits. Then after that 4 bits, we still have 8 chunks. That's why the output goes back to 32 bits. So that is the basic F function here. Also, there is a P function. After that, we have 32 bits. The 32 bits go to the P function to rearrange those tables. So next, let's look at one of the S tables. So this table is the S table 1 of the DES design. So this is hard-coded in the DES design. This one never changed. Yeah? So you are talking about the expansion function. So the purpose of this, because the input was 32 bits, right? How does that? I don't have that in my slides. So, but basically, that is also some deterministic algorithm, obviously. There's no randomness there. Yeah. Yes, P function also has a table. Yeah. So the S function here, this S box, one of the S box looks like this. So how do we read this? So let's say the input here is 6 bits input. So we read this as, let's say your input is bit 1 to bit 6. Then the row, there are 4 rows. That's why there are 2 bits, right? So from 0, 0 to 1, 1. So 4 rows. And the column, we have 4 bits, which is 16. So this table has 64, so 4 times 16, which is 64 possible inputs, which is 6 bits, right? Then the output will be the value inside the table. And you can see the value inside table is smaller than, we don't have something like 64, 63, right? So the value, the biggest we say here is just 15. 15, from 0 to 15, that's only 4 bits, right? So the output is actually reduced from 6 bits to 4 bits. And some of the output, you can see, repeat themselves. There are 15 appear twice, no, more than twice. 1, 2, 3, I can say multiple 15 there, multiple 14 there, which means if let's say this one, which is 14 here, which means if the input is 0, 1, 0, 0, 0, 1, something, then the output will be 14. So you just replace that. So this is just a simple mechanical substitution. So that's what S-box works. And this one, you can say the S-box here doesn't really, it's not directly related to the keys, because this is already after you exclusive or with the key. So for those who took my software security course, we actually talk about, you actually did cache side channel attack. In cache side channel attack, one of the application of that is to steal crypto keys. And how we do that is we have the S-box in the process memory, and we try to use cache side channel to compute which items of those S-box has been recently used by the program. Then from there, then we can know what is the input of the S-box, because we know which one is accessed. Then we know which one is the input. Then going back to the input, you can say, so the input of the S-box is here. Then we have the original plain text. Then we can infer what is the subkey. Then from the subkey, we can infer what is the master key. So that is the rationale behind applying cache side channel attack to break crypto. Obviously, that has nothing to do with crypto analysis, right? Crypto analysis is finding the vulnerability of the algorithm design. That the attack I just described is to find the vulnerability of the implementation, not really the design of the algorithm. So a little bit more about the S-box. So the S-boxes in the standard were a little bit different from IBM's original design. And the design rationale behind the S-boxes were not public. For example, when you look at this, how can you explain why we choose 15 here instead of 13? IBM didn't explain that. Because of that, it actually somehow it breaks the Kirchhoff principle. You're not disclosing every design principle of your algorithm to the public, right? Even though you are designing how it works, but your design didn't disclose the principle. Okay. So in the after DES was widely used in the 90s and in the 80s and 90s, there was a branch of crypto analysis called differential analysis. They were discovered, which means you have a plain text, you change the plain text a little bit. So you have two different plain texts. Then you observe that two different plain text, how they will influence the encryption process. You monitor all the steps, trying to find the correlations between different bits. However, it was found that differential analysis on DES was not easy, and people find out the S-boxes actually can prevent a lot of differential analysis there. So this is very interesting. This is before differential analysis was publicly disclosed, which means maybe IBM or NIST. So before the public, the research literature know something about differential analysis, they already know that. Okay, so this actually happened multiple times in the crypto history. So another one of the most important crypto, when we talk about public key crypto system, was also designed in the 70s. Then some MIT guys, they published a paper, and the world was shocked. Then 10 years after, the National Security Agency claimed that we actually invented crypto system, the public key crypto system, 10 years earlier than you. But no one can really prove that. But I kind of believe that, because government, they cannot disclose that. They do not really get the credit. For example, the professors who behind the public key crypto system, they got a Turing Award. But probably they were not the first ones to design that, if you believe NSA's claim. But whoever behind the NSA's design of public key crypto system do not really get any public recognition even today. So also for the DES keys, we said that the master key is 56 bits. However, for each round, it's 48 bits, and there are 16 rounds. So how do we generate those subkeys? What we do is we also divide the key, the original 56 bits, into two parts, C and D. Then each part is 28 bits. Then we shift the keys. Shift is here is just kind of like rearrangement, right? It's permutation. Then goes through more permutation and generate the 48-bit key here. So in DES, people discovered that there were several weak keys. So if you use those keys, basically because we are extending the 56 bits of keys into someone much bigger, 48 times 16, right? And some weak keys, because the way we expand those keys, some of the subkeys will be much more predictable. So some keys, they result in the same subkeys to be generated more than once. So you do not get 16 unique keys, subkeys. Some of them repeat there. So people discovered at least there are 4 weak keys, and it's all 0 or all ones. I believe there are more, but those are the widely known ones. Also, because the design of S-Box was not disclosed at the very beginning, people suspect that IBM or NIST may implemented some backdoors. Maybe there are some keys which is universal, can decrypt anything. Yeah, question? How do we, you mean why do they want 48? I don't really know why they designed like that. Yeah. So here we're not really reducing from 56 to 48. The 56 bits, that's a master key. So what we're doing is we have 16 rounds. Each round has 48 bits, which means the real key used is 48 times 16. That's much larger than 56. But the real seed is only 56 bits. Yeah. So attack on DES. Well, there is a typo. It's not 256 keys to the 2 to the power of 56. That's a big number. So DES itself was quite secure itself. The design principle there is still solid for today. However, the key space is a little bit small. 56 was considered pretty secure back in the 70s. Well, I mean, back in the 70s, probably Bill Gates said hundreds of kilobytes of memory is enough for everyone, right? So it was considered very safe back then. However, obviously, it's not safe now. Even though the algorithm itself is quite safe, brute force, all the keys 2 to the power of 56 bits, it's not a very difficult job for now. Differential analysis, which has been quite successful on a lot of algorithms, was not very effective against DES. So DES was quite safe, secure. The only problem is the key is not long enough. And because of that, before that. So basically in 70s, people think if you build a machine to crack DES to enumerate all the keys, that machine probably will cost you $20 million. That's back in the 70s. Then in the 90s, RSA Lamp, which is a company, so everyone in security knows this company, and you can see it's called RSA Lamp, and RSA is one of the important first public key crypto system. We're still using it today. And so the inventors of that algorithm founded this company, RSA. I believe this company is part of EMC right now. So this company, they called for a DES challenge to ask people to build machines to break DES. So you can say there is a financial, obviously a scientific and also financial motive behind this, right? Because they want to promote public key crypto, so they want to break traditional symmetric crypto. So in 1998, organization EFF, they designed a machine for $250,000, and they can break DES in 56 hours. A year later, another more like a distributed computing approach, collecting 1,000 computers worldwide, was able to break DES in 20 hours. So now I believe even use your laptop, we should be able to break DES. We just enumerate all the keys. We can do that in 20 hours. So because of that, there were several other proposals to increase the security of DES. But like I said, DES itself is quite safe. So when we say increase the security, it means we somehow want to make the keys longer. That's why there are some very simple proposals. The idea is very simple. However, they work. Okay. Basically, you just run DES twice or 3 times. Use different keys. Then technically the key length will be twice or 3 times longer, right? So one of the proposal was called a double DES. You just apply DES twice using 2 keys. You encrypt with the first key, then you encrypt it with the second key. So technically, the key length here is 112 bytes. But someone find out an approach called meet in the middle attack. They find that here's a lot of typo. Sorry about that. So the man in the meet in the middle attack find that the key length is not really equivalent to 122 bits. It's still more secure than 56 bits, but it's not as secure as 100. It doesn't really double that. That's why there were other proposals, and there were 2 triple DES proposals, and those algorithms still now we don't know some other practical attacks against either versions. The first triple DES only use 2 keys, so the key technically the practical key length there is 112 bits, but we are using the first key to encrypt the message, use the second key to decrypt the message again. So then we use the first key to encrypt it again. That's how we do the real encryption. So the decryption is just the reversed operation like that. Another approach is just use 3 keys. The first we encrypt, then we decrypt. So here just using the encryption algorithm, using the decryption algorithm, and use the encryption algorithm again. So this one is 168 bits. So that's basically the methods to improve DES. However, DES is not used anymore. Now, most of our systems, we use AES, and also our CPUs integrate, many of our CPUs integrate AES. So there is an instruction in your CPU called AES encryption. A lot of CPUs can do that. Yeah, question? No, because you are using a different key. It doesn't give you the plain text. It's just it just give you some other ciphertext, some random bits. Yeah. So next we talk about AES. So AES was there was a formal solicitation. Liz did it again in the 1997. They asked for a new publicly disclosed encryption algorithm that we can use for commercial use. And it's royalty free, means everyone can use that. That's why it gets so popular. The goal was to replace DS. And their requirement was we want to have a symmetric block cipher. And the algorithm have several different modes to support different block size and key size. They ask for 128, 192, and 256 bits of block size and key size. I think the block size is always 128. The key size could be different. This is actually very important. So which means AES doesn't support 69 bits of keys. So 128 is 16 bytes, right? 156 is 32 bytes. They do not support shorter keys. So why I want to mention that, because in one of the challenges 2 years ago, my team, we were doing an embedded system CTF challenge, and we use AES to encrypt our system. However, we run AES on a very low-end microcontroller, so it's a little bit slow. So one of my PhD students think it's too slow. I want to make the key size shorter. So instead of 128 bits, he just changed the key size to 96 bits, which AES doesn't support. But the library, the software library, AES library she was using, do not give any error. It's just do not encrypt. Input, then give you the plain text, goes through AES, generated output. The output will be the same as the input. No encryption, doesn't give any error. And we didn't realize there was an error in our code. So we designed a system, spent 2 months designing a system, put it online, then several hours later, I believe CMU cracked our system. And we had no idea how they cracked AES until a month later, they said that we used 96 bits of AES, which doesn't exist. Okay. So remember those numbers. So AES was designed a little bit different from DS. It tries to be very fast, and also it doesn't really use the faster network anymore. So for AES, we still have each block. Let's say each block is 128 bits, which is 16 bytes. We divided that 16 bytes into this state matrix. So each one could be just 1 byte. Then each round, we are going to change this matrix. So the matrix is not really different from an array or something, but later you will say there is one operation, you will say why they divide it into matrix, because for us, it will be easier for us to understand. So for each round, the input will be 16 bytes, but looks like a matrix. Then we are going to do substitution and permutation on this matrix. The AES key also will be treated as a matrix, and it is going to be expanded into subkeys, same as DES. Each round there will be a subkey, and we call the smallest unit in a subkey we call a word, and each word is 4 bytes. You don't have to remember those numbers. So the idea of this is just for you to get a feeling how this is designed. Those numbers are not that important. So the AES algorithm we are using right now, the original name is called, I don't know how to pronounce this, Redale maybe. So this was the candidate algorithm's name, is this one. After it's accepted, we call it AES. There were multiple candidates. Two of the, there was obviously several rounds of selection. And the final 5 candidates, 2 out of the 5, they didn't really using that Phaster network. But still, 3 of them were using Phaster network. So AES, the other 2, they can process the entire block in parallel. So the benefit of this is it can be faster. Okay, you don't have to be. So you go, if you go back to the Phaster network, you can say here. So the left-hand side has to wait for the right-hand side to finish. Then they can do the exclusive OR. That's why there is a sequential operation. You have to do this one, then this one, right? Because of that, we want to remove this structure so it will be faster. We can do things at the same time. So going back to the slides. So the AES has 4 main operations. But they are just the substitution and the permutation. There are basically 3 substitution and 1 permutation. There is substitute bytes, byte by byte substitution using predefined S-box. There is shift rows. So this is a simple permutation. There is also mixed columns. That's also a substitution using mod 28 operations. Also, add round keys is a simple exclusive OR with current state with the subkeys. That's actually the last step is the only step that uses the key. All other step has nothing, doesn't really have anything to do with the key. So at a high level, the encryption works like we have an initial state S, which is that 4x4 matrix. Then we perform the add round key operation. We get the subkey for this round. Then for each round, we perform a substitution operation on each of that 4x4 matrix to replace it with another number. So we use S-box to do that. We look up in the S-box to do that. Then we do a permutation shift. Then we do a mixed column operation on each of them. So, like I said, only the round key step we use a key. So all the operations are reversible, which means the decryption algorithm would be very simple as long as you know how to implement the encryption algorithm. So sometimes maybe they can be the same function. If you implement this in software, maybe they are the same function. If you implement hardware, it may be just the same hardware module. You just need to change the keys. So the sub bytes will just use S-box to substitute each byte. And because the input is 4x4, the S-box is also it's a bigger matrix with a byte in each position. So this is basically what the S-box looks like. We already seen the DES S-box. This is similar to that. What is different from DES is AES have this shift row operation. So let's say this is the input of shift row. We have the 4x4 matrix here. In this shift, the first row, we're not going to shift anything. The second row, we're going to do a left shift 1 byte. So this one, S10 goes to the end. S11 goes to the beginning. Then the third row, we're going to shift 2 bytes. The fourth row, we're going to shift 3 bytes. So this is how the shift rows operation works. This is unique, different from the DES operation. Then the mix column operation just multiply the state with a fixed matrix. So the decryption is just reverse all the operations in each of those steps. And key expansion was also designed to resist some known attacks, and also at the same time try to be very efficient. So this proposal wins the competition and becomes standard because it's a very simple design. Looks like everyone can understand. However, it is resilient to all known attacks, and it's very efficient. It can be parallelized there, so has a very high throughput. This is used in all our systems right now. Like I said, a lot of our hardware, the CPU, have this instruction directly. Like the Intel CPU, they have a AES-NI instruction, so you can encrypt things very fast. However, all those crypto algorithms, block cipher crypto or block encryption, there is a problem. What we encrypt here is just one block. So in AES, DS, one block is 16 bytes. We are only encrypting one block. But the data we encrypt, obviously, it's much larger than that. So what we do is we need to partition our plain text into smaller blocks. Each block is 16 bytes. Then we encrypt each of them independently if we only use the AES or DES algorithm. And this brings a problem. It doesn't, so each block is encrypted independently. So if two blocks, they are the same. After encryption, it will still be the same, right? Let's say we have a picture of the Linux logo. There is a block. This is a bitmap. That block may be just all zeros. Then there are many all zero blocks there. Let's say one block is 16 bytes. Then there are many 16 bytes. They are all just, it's white. The data is just all zero. So after encryption, you use different keys to encrypt. However, after encryption, they will become the same thing. So after encryption, you can still see a pattern of the original data. Even though you do not see this plain text shows some pattern there. And it may also be used for some replay attacks. So that's why on top of block cipher, we introduce encryption modes. And in the original DES algorithm, DES crypto, there were only 4 modes. In AES we're using right now, we have 4 modes. We have the 5 modes. We have the 4 originally designed for DES and a new one called counter mode. And the counter mode is the one we use a lot today, or the variant of counter mode, because later you will see the counter mode is super fast. It's faster than all other modes. The first mode is the original one. We just encrypt, we have a message. The message is very long. We divided the message into smaller blocks, each block 16 bytes. Then we use the same key to encrypt each block independently. This is called the electronic code book mode. And this figure I'm showing you here is using this ECB mode. So nothing special about this. This is now secure. Anyone use, if you are using any crypto library to encrypt anything, do not use the ECB mode, okay? This is not secure. Then we have the cipher block chaining mode or CBC mode. In this mode, we have another random number we call IV, or initialization vector. IV is not really a secret, but it has to be random. IV itself doesn't have to be encrypted. It's not a secret. When you communicate with another party, you do not send your keys because key is a secret, right? So you somehow negotiate the key or you distribute the key before this encryption. You send them the ciphertext and the IV. IV is in plain text. It doesn't have to be encrypted. It should not be encrypted, but it has to be random. Then for the encryption, what we do is we are going to, let's say, for the very first message, 16 bytes, what you do is you will do an exclusive OR with the IV. After that, you will encrypt use AES using your key. So even if then after that you get a ciphertext, right? So the ciphertext will be used to do another exclusive OR operation with the second 16 bytes of the original plaintext message. So even if M1 and M2, they are the same here, you can say the output of C1 and C2 will be different. So this is different from the ECB mode. If M1 and M2, they are the same, then the output of C1 and C2 will be the same because they go to the same deterministic algorithm and using the same key, right? So using this CBC mode, we are not going to have the same problem as the ECB mode. But there is a problem with this approach. The ECB mode, you can say, those are totally independent steps, which means you can run them at the same time. You can encrypt M1 at the same time, encrypt M2, M3, M4, right? So it will be very fast. But in this CBC mode, you cannot do that anymore because the encryption of the second block relies on the output of the first block. You have to encrypt the first one, then feed the second operation with the output of the first one. So it will be strictly sequential. It will be very slow. The other two modes are similar. One is called a cipher feedback mode. In this mode, still very similar. We have an IV. We encrypt the IV. Then we use the same key to encrypt the IV. The output of IV, we will do an exclusive OR with the message. Then we get the C1. Then the output will go to the second block. As you can see, this one is quite similar as a string cipher because the cipher, your encryption, your original plaintext message, that message never goes into the AES or DES algorithm itself. It was just do a simple exclusive OR with the output of the encryption algorithm. Okay, but this one is still sequential, you can say, because the output of this one, the first step will go to the second step. So this one is also a little bit slow. The third one is called a cipher feedback mode. This one is called this one is still cipher feedback mode. Yeah, this is just more details about that. Let's say another one is called output feedback mode. So what this one does is we have the IV. IV will go to the encryption. Then we are going to select some bits here. Then some of the bits will go to the second round. Some of the bits will be used in the current round. So, but still, it's sequential, right? So that's why we desperately need something fast, something we can encrypt each block independently. And so that's why we have the counter mode. And the counter mode and also the in AES, if you use a lot of AES libraries, there is a mode called GCM. It's based on the counter mode. It's a little bit changed a little bit, but almost the same as the counter mode. So this one, the operation is very simple. You have a counter, okay? You have a counter. The counter can start with a random number, like the previous IV. It started with a random number. It doesn't start with 0. Same as the sequence number in TCP. It doesn't start with 0. It started with a random number, okay? Then for each round, I should not use the word round, because round means inside the encryption. For each 16 bytes, we just increment the counter, which means add 1 to that counter. So let's say the counter at the beginning, we get a 100. Then for the first 16 bytes, we encrypt that. We just get a counter 101. We encrypt 101 using the key. We get the output. Then we use the exclusive OR on the plain text message and the results of the counter. Then we generate the cipher. The second 16 bytes, we are going to use counter +2. So which means for each block of the plain text, we know beforehand which counter we want to use, as long as we decided the starting value of counter. So we can calculate all the encryptions at the same time. So this is very fast, and it's a little bit surprising that this one is as secure as other approaches. Okay, intuitively, you look like this. You may think, okay, this looks like the ECB mode. It may not be as secure as those OFB mode or CFC mode, but someone proved they are actually equally secure. So, but the benefits here obviously is huge. So this is a counter mode. So when you program, you are very likely to use counter mode or a variant of counter mode. They are more like mass approaches. You can imagine it's more about probability, right? So basically, you need to prove that the correlation between the plain text and the ciphertext is very low, or statistically they are not. There's no significant link between them, right? Then you can quantify that, use mass, right? I'm not really a cryptographer, but if you you need to read some papers to answer that, yeah. Okay, so summary of the class. AES is still the one we are using. And when you use AES, you need to pay attention to the encryption modes and also the key lengths, obviously. So strong randomness is required for crypto operations, which means the key should be random because the algorithm is public. The IV should be random. The counter should be random. This is not a problem for most of our laptops or servers we are using, because those devices, they have some built-in, what are they called? Random number generator, right? However, this is a big problem for some low-end embedded devices, especially my lab works on low-end embedded devices. We find that's a big problem for us to design a secure system. For the ones you took my software security class, you remember to defeat buffer overflow, we have a mechanism called stack cookies or stack calorie. So basically, it's just a random number you put on the stack between the return address and a buffer. So if attacker overrides the buffer, they have to override sequential override. They have to override that random number. Then later, when you do a return instruction, you will check that random number if that random number has been modified. However, we find out this simple approach on those no-end devices may not work anymore, only because we don't have randomness. We don't have any random number generator on those no-end devices. So the entropy we generate for stack cookies is really low, which makes it not really secure. So that's all I have for symmetric key encryption. So Wednesday, we talk about hash functions. Any questions? Oh, there is a attendance check. I don't know who has that. Just sign your name there and pass it around. Okay, if no other questions, see you guys Wednesday.